Okay, so for chapter 10, we are going to be talking about what's called a one sample hypothesis test. And over the next several slides, we'll show you how to write the test and how to come up with your decisions on when you're basically making your inference about the population from the sample. So first things first, a hypothesis is basically, again, it's some sort of statement about a population parameter that's subject to verification. Now, that verification is where basically we're going to be taking a sample, okay, and the sample again will be given in the problems. And then what we're going to do is we're going to look at that sample and study it and then make a conclusion about that population. And some examples are given down below. And so whether you're trying to prove a product label or evaluate a performance, it's going to allow you to come up with some sort of scientific statement that's going to allow you to make decisions or predictions about what you're trying to achieve. And so they do give you a list of steps in this book in terms of how to set up your hypothesis testing, again, taking samples to evaluate the population. And you notice the first step we're going to talk about is what is a null and alternate hypothesis. And then we'll talk about this thing called, selecting a level of significance. And you'll find out that later on we're going to refer to that as that's an alpha level. And then, of course, the next step is to identify the test statistic. And so, again, you got to identify what you're going to be sampling. And then you'll have the decision rule. The decision rule is going to be related back to this alpha level, by the way. And then, of course, we'll take the sample. We'll compare that sample, do some analysis on it, and come up with a decision on whether to either reject or accept the null hypothesis. And that'll be the last step when we get to the step 6. So again, the way these things are typically labeled is the null hypothesis is labeled as HO. And then, of course, you're going to have what's called an alternate hypothesis. And in this textbook, they're going to label it as H1. And you're going to find out that the way these are set up is that they're actually mutually exclusive. And so that when we do take our sample and we do come up with our conclusions, we're either going to be saying we're going to either accept the null or reject the null. And we're basically saying which of these two statements does the sample support. Is the sample basically supporting the null, or is the sample going to be supporting the alternate hypothesis? Now, this thing called the level of significance, I'm just going to kind of reinforce this. This symbol here is called the alpha symbol. And in every problem, again, it's stated right down here, typically they're going to give you some sort of percentage. And this is going to basically be part of the criteria when you get to making your decisions on whether to reject or not to reject the null hypothesis. But again, it's called alpha level. And you're going to find that basically this alpha significant level is going to be tied to what we call a critical Z value or a critical T value when we come up with our decision rule. And of course, we'll get into this a little bit later, but of course, anytime we have a significance level, which again is going to be alpha, and we get to if you look at your conclusions, which are you either do not reject the null or you reject the null, there could always be errors because remember, you're still taking sampling, and samples isn't always the whole population. So these just talk about there's what's called a type 1 error versus a type 2 error. And you're going to find out that typically type 1 errors are consistent typically with a rejection criteria of the null. And the type 2 error are going to be consistent with the do not reject of the null. And typically those are tied together. So you never can actually have both types of errors together. So typically anytime there could ever be a type 1 error committed, it always goes with reject the null, and the type 2 error always goes with the do not reject the null. So the next step is obviously you have to determine where or what are you going to take your sample, and that's basically they say to identify the test statistic, and that's basically you're going to try to figure out what are you going to try to extract from the sample, and typically we're going to get either a sample mean in this particular chapter. Typically for a sigma known or sigma unknown scenario. Of course, if we were looking at a proportion, which they do that actually in chapter 15, we would have a p-value. But basically, you're going to be taking a sample, and then basically, based on that sample, you're going to be converting it either into a z-value or a t-value to come up with your decision rule. And of course, if you look at this particular slide, they give you all the basic different ways in terms of to come up with your conclusions. You'll notice I'll label this first one. This is what I like to call a lower tail test. The middle one is what we like to call a two-tailed type of test. And this third one is typically what they like to refer to as an upper tail test. And the basic idea is that if you see whatever area is shaded under all these different types of hypothesis tests, that area is always going to be referred to as the rejection area of the null. And then also those areas are also referred to as the alpha level, okay? Or if it's a two-tailed test, obviously it'd be alpha half. But again, that area is going to be the rejection area, which is also called your level of significance. So the basic idea is once you get your sample, you convert it into a test stat, which is going to be either a z-value or a t-value. And depending on one of these three types of scenarios that you're testing, if that test stat falls in a shaded area, your conclusion is going to be reject the null. Now, of course, obviously you have to get into, how do you take a sample and those kind of things. But basically, you take a random sample, you calculate it, you convert it into the z-t value, and at that point, you're going to either say reject or do not reject the null. Again, basically based on that level of significance that you set up already. That's going to basically be the whole thing that your decision is going to be based on. And then finally, obviously, once you've made your decision, you'll go back and then do some analysis and decide if you might need to take another sample if you're not convinced that your first sample was relevant in terms of how it represents the population. But that would be the final step, is basically to do your analysis. Okay, so in this first example, this is going to be a sigma known scenario, okay, because if you read through the problem, they're going to give you the population standard deviation. It's going to be 16. But the question would be, so you read this thing, and it's talking about a weekly production, and it's normal distribution, and they're talking about trying to see if there's been a change in the weekly production of this particular product. And the key word in this problem is going to be a change, which means, is there any difference? So typically, when you see keywords such as change or differed, you're going to find out that that always typically goes with the two-tailed type of hypothesis test. And of course, again, this is a pretty good slide. It kind of gives you some ideas in terms of how to recognize the different types of hypothesis tests. And obviously, if you look over here, where you got the equal to, not equal to, notice, look at the key wording. Difference, has something changed or not changed, and so forth. And typically, that's going to be very indicative of the two-tailed types of tests. Usually, the two-tailed types of tests are the easiest ones to identify. So now, if you look at these scenarios, notice you've got scenario number 1, number 2, number 3, 3 different ways to set up your hypothesis statement. And of course, on the previous slide, we just identified that that was going to be a two-tailed test. And notice they give you your rejection criteria under each of these. And so we're going to be following this rejection criteria for the two-tailed test. Now, of course, down below, you see both of these two calculations, guys. That's basically how we're going to calculate our test stat. And you notice it really depends on if it's going to be a z-value or a t-value. And your basic thought on that should be, just ask yourself, if sigma is known, it's always going to be the z. If it's going to be sigma unknown, then you're going to be looking at this formula. So just use that as your simple rule and you'll be fine. Now, of course, this kind of gives you all the different characteristics about the null and the alternate. And I'll just kind of highlight a few of them. Is that basically the big ones is that HO and H1 are mutually exclusive, which means that if you look at the basic way these things are set up, notice you say either equal to or not equal to, okay? It's either going to be greater than or equal to or less than. It'll either be less than or equal to or greater than. So it's always mutually exclusive. And typically, the other big thing I want to focus on is typically you're looking, when you take the sample, you're basically trying to reject the null. That's what you're actually going to be trying to do. So in some cases, when I give you some examples, sometimes you might actually want to write the alternate first because if you can get the alternate, you always know that the null is going to be completely the opposite. And I guess one more thing I just want to make a note. Notice that as you compare all of the different scenarios to write the hypothesis statements, is that it's the null hypothesis that always contains the equal to type of sign. That's kind of a big thing. So that's very, very consistent on all the statements, is that the equality is always in the null, and so therefore the inequality statement is always going to be in the alternate. So going back to the example, we said this one, the key word there was change. And so notice they stated the null and the alternate as being equal to or not equal to. And again, of course, they're saying the key word there is change. They're going to select a significance level of alpha to be 0.01. So just to kind of give you a preview, I like to always draw my curve just to kind of get the thing set up. And I'm going to have two tails of rejection. And the key thing about the two-tailed test is typically anytime you have alpha, you want to divide it in half. So if you take 0.01 and divide it in half, each of these two tails is going to be 0.005. So each tail is actually representative of alpha half. And so just remember that those tails also represent the areas of rejection of the null. Okay, now the next thing you didn't want to do is you should be able to get what's called your critical value. Your critical values are based on this alpha level. And then just always remember that because again this is sigma known, we're going to be looking in the z table. So these values for the critical value, these two numbers, are going to be extracted again from the z table. Now, so your formula for the test stat, again, remember I said before, because this is a sigma known scenario, this is going to be the equation you're going to be using. And you've done this before, x bar minus mu divided by sigma over the square root of n, and that's going to give you your test stat z value. Okay, so if you look at the actual data they're trying to show you, so remember, right down here, guys, this is going to be your calculation to convert that sample into a test stat. So they ended up getting 1.55 as their test stat number. Now, if I go back, you guys see the 2.58? The way they got that 2.58 is if I go back to my curve, remember in the previous slide, I said that each area was 0.005. So quite literally, you were looking up, if I again divide this curve in half, you would be looking up 0.495 in your z table, and that would correspond to either a plus 2.58 or a minus 2.58. So that's how they're arriving at this value. So then your next step is simply to compare this test stat, this 1.55, to see if it falls in a rejection area. And as you can see, it does not fall in a shaded area. So because it does not, your conclusion is going to be do not reject the null. Okay, so the next example for hypothesis testing is going to be a sigma known population standard deviation and a one-tailed type of test. So in this particular problem, as you read through it, they're talking about improving production methods, and they're trying to conclude that if the average or the mean number of desks assembled in the last 50 weeks was, and here's in bold the key words, is more than 200. So again, that's going to be the key to how you set up your hypothesis statements. So again, sigma is known at 16, sample size is 200, and then this is also going to be important. This alpha level will determine your critical value for your decision rule. So again, as you can see, this is going to be a one-tailed, or what we call an upper tail type of hypothesis test, because they're looking to see if the production has increased. So look at how they have basically set up the null and the alternate. The alternate is the greater than, because that's what you want the sample to support. And the other thing is you notice, you see this little critical value that says 2.33. That's going to be associated with this alpha level of 0.01. So the basic idea is to get this 2.33 in your particular tables. Obviously, you're going to cut it in half because you have the half table, and you're basically going to be looking up 0.49, and that's going to give you that critical z value of 2.33. And then once you get that set up, then you do your test and you can come up with your conclusion. So again, they're just to kind of reinforce this again, because we're looking for an increase, we want the alternate to say greater than. And what I tend to like to do is also, just to kind of give you the visual, I'll draw the curve again, and I'm going to shade the upper area of the tail. That area is 0.01. You look that up in your table to get the z value. In this case, it's going to be about 2.33. That's going to be your level of significance, is going to give you that number. Now, the next step is really to calculate the test statistic. So here's your formula, and again, this actually is sigma known, guys. That's not sample standard deviation. It should be actually sigma known. And so in this case, they came up with a test stat that's equal to 1.55. They use this equation to get the z value. They then are going to compare that with that critical value. Again, I'm going to say this really is going to be 2.33 just to be consistent. But again, because this number is not in a rejection area, your conclusion will be do not reject HO, or the null. Now, another calculation they're going to have you do, and this is also going to help you come up with the decision, is to calculate what is called a p-value. Well, the p-value, I'm going to make it way down here. The p-value is simply your test statistic, okay? So it's going to be your test stat that you're going to convert into a cumulative probability. So the basic idea is whatever number you get for your test stat, you simply go to your probability table, and whether you're looking to the right of that particular value or to the left of that particular value, you're going to basically get the area or probability, and that area is going to be called a p-value. And then what you typically do with that is you're going to compare it with alpha, which again is your significant level. And this is really your true decision rule, is you always reject it if the p-value is actually less than or equal to your alpha level. So in this last particular problem, you notice we had a z-value, or this is your test stat z-value of 1.55. And of course, if you look at where this fell under the curve, it fell right there. So to actually get the p-value, what you do is you go to your z-table, you look up 1.55, and of course, you want the area to the right, not to the left. So when you get that area from your table, you're going to find out that that area to the right of that particular value is right here, which is 0.0606. So then you do the comparison. Is that value less than or equal to alpha? And of course, that is false. It is not. So you get the same conclusion, which is do not reject. So just to kind of go back, if this p-value were, if it's true, if it would be less than alpha, then you would reject the null. But because this is not, that's why you say fail to reject the null. And this slide is just kind of giving you some clues on terms of, what happens when you get larger or smaller p-values. And again, it all comes down to comparing it to your alpha level. But typically, a higher p-value, you're typically going to say you're not going to reject the null. You're going to say it's true. Smaller p-values like this one, typically you're saying the null is not true. Smaller p-values, you get more of a what you call a rejection rule. You're going to reject null. A larger p-value, you're most likely going to say do not reject the null. But again, it really depends on what you're comparing it with. The alpha level or significance levels really determines what's going to happen with your outcomes. Okay, so for this particular example, we're going to go over to the other type of scenario, which we call the standard deviation, which is unknown. Again, sigma unknown. So you're basically going to be using the sample standard deviation. So here's our formula. Notice it's essentially the same, except we're going to be using S instead of sigma, and we're going to be calculating a t value rather than a z value. So we're going to go back to the t distribution table, and down below you can kind of see what we need. We need the degrees of freedom. I always label that as df, which is n-1. We'll need that alpha level, the significance level, to get our t value, our critical value. And then, of course, the actual calculation when we do our test stat is actually going to be just pretty much the same as the sigma known. And so, again, using this sample, they give you, it's going to be a sample of 26 claims that were processed. And they're trying to conclude, and here's the key words, is if a claim is actually going to be less than the $60 to process the claim. And they're going to be using a significance level that's 0.01. So alpha is 0.01, okay? Our sample size is 26, and the hypothesized mean is 60. And so then they give you the data. So what you literally have to do is you have to figure out, first of all, what's the sample mean, and you have to figure out what is the sample standard deviation because they didn't give it to you, but you have enough information here that you can actually calculate those. And so to set up your null and alternate hypothesis, notice here's our setup, and the keyword was less than, so you want your alternate to be less than. So I always call these are typically referred to as a lower tail test. We've got the alpha level, so this number up here, this area is going to be 0.01. So now simply you have to get a value here to help you come up with your rejection rule. And so what you're going to be needing here is alpha and your degrees of freedom, which in this case is going to be 25. You take this and the alpha level, you go to your t-distribution table, and that's going to give you your critical t-value. So in this case, because again, this is a one-tailed test, 0.01 is right there, 25 degrees of freedom is right there, and these intersect right here. So 2.485 will be your critical t-value. And as you look at this test, because it is a lower tail test, you want to put a negative in front of that because it's negative, it's going to be less than the mean. And so then over here, here's essentially going to be the calculations. And they went ahead and just gave you the sample standard deviation, but obviously you'd have to calculate that number, but they just gave it to you. But they came up with a sample test stat, or test statistic average, or z-score, I'm sorry, that's about a negative 1.818. And so once you get that, you'd compare it to your critical t-value. Notice it's not in a rejection tail. So again, you're going to say, do not reject the null. Okay, and so for this particular example, it's another sigma unknown scenario. And again, the key word here at the bottom, I'm just going to jump right to the bottom once you read through this, is that they want to conclude if the new machine is actually going to be faster. Okay, so it wants to be faster. And so if they're producing, in this case, 5 amps, if they're producing 250 per hour, and they're going to randomly take 10, and the idea is you want to see if you're going to be producing more per hour. So you'll be thinking that you want your alternate to be a greater than. It's the greater than idea. That's what you want your alternate to represent. And as you can see from the setup, this is how they set up the no alternate. Notice the alternate is a greater than. So I'll draw my curve. This is going to be an upper tail test. 0.05 is my significance level. And so to get your t-value, your critical t-value, you need your degrees of freedom, which is going to be 9, plus your alpha of 0.05. And in the next slide, once we look that up, we'll show you what that critical t-value is going to be. And so, of course, you got to calculate your test stat. And in this case, your test statistic, here's your basic formula right here. You get a 3.162. And of course, you have to compare that with your critical t-value. And in this case, if you look up your 9 degrees of freedom with an alpha level that's 0.05, and again, let me draw the curve picture just to kind of give you the visual. So we're saying that that t-value is going to be 1.833. That's based on alpha of 0.05. Once you get that test stat, you notice that is in a rejection area. So you're going to thus say that the null hypothesis will be rejected. Okay, the last kind of final things to talk about in the chapter is what they call the types of errors. And just make sure you know that a type 1 error is basically goes with the conclusion of whenever you reject the null, there's a possibility of a type 1 error, and that probability is going to be whatever alpha is equal to. And so the type 2 error, which is the other type of error, goes along with the conclusion of do not reject the null. And basically, it's whatever your p-value is. Your p-value is going to be the probability of that type of error. And so often they call that a beta error for the type 2 error, and the type 1 error is often referred to as what they call the alpha error. And so if you just kind of look at the basic definitions of each, you can never commit both errors at the same time. It's either you could have made a type 1 error or a type 2 error, depending on your conclusion. So again, a reject null conclusion, there's a possibility of a type 1 error. That possibility is whatever alpha is. If your conclusion is do not reject the null, then of course you couldn't make a type 1 error, but you could only possibly make a type 2 error, which is called beta error. That probability is going to be whatever the p-value is.